Hello there. We're going to talk today about batteries and the cells that make them up. So, first of all, what is a battery? A battery is two or more cells, like you made in your lab, that are connected together, and when they're connected, they produce electricity. A battery is just a can full of chemicals that produce electrons. Those electrons go through something and they have an effect, like light up light, like you guys saw. So every battery is going to have two parts in general, two terminals. There's a positive side, that's the cathode, and there's the negative side called the anode. We're going to talk a lot more about those later, what makes it positive, what's not. Double A, C, D cell batteries, which you're probably familiar with. The ends are the terminals, but in like a large car battery, there's going to be two lead posts that act as the terminal. They're usually called lead acid because they've got an acid in there that is the electrolyte. And that's the next thing that batteries need. But I want you to ask yourself a question, see if you can recall. What's the difference between the anode and the cathode? Think about it. Right? Hopefully you said the anode is going to be the negative side, the negative terminal, and the cathode is going to be the positive side. I want you to think of that cat again and that and again. It should remind you of what we've talked about before. Cats have paws. The positive side is the cathode. So, what are electrolytes? I said that's another thing that you need in a battery. An electrolyte is just ions that dissolve in water. We've talked about ions before. That's where you've got more electrons than protons, or more protons than electrons, and something that goes into water. And like an ionic compound, when it goes into the water, it breaks down into ions. And so there are different types of electrolytes. There are, sodium hydroxide, sodium chloride. That should sound familiar. That's salt. Hydrochloric acid. That's in your stomach. Water is actually a weak electrolyte. Acetic acid, like vinegar, ammonia is. But sugar, alcohol, and oil, these are non-electrolytes. They will not break down in water. And so you can have more than one flavor of electrolyte. You've got the cations, the major positive ones. That is sodium and potassium and calcium and magnesium, to name some examples. And then there's the anions. Those are chloride or bicarbonate or phosphates or sulfates, like a lead acid battery. And so these are going to be important because these are going to actually determine which one's the cathode and which one is the anode. That's where the anions are going to go, and they're going to make it positive or negative. We're going to talk more about that. But I want you to look at this label here and see if you can figure out the sports drink. What are the electrolytes? What are they actually referring to? Okay. Well, hopefully you saw in there that there's salt, that's sodium chloride. And then there's phosphate, monopotassium phosphate. The citrate in the sodium, this is sodium's a cation, citrate's going to be an anion. Potassium is a cation, phosphate's an anion. So these are actually, when you're drinking a drink for electrolytes, this is what you're taking in. So in general, what happens to electrolytes in batteries? Why do we even need them? So we're going to talk about it in the type of battery that you guys made, the zinc ion or the aluminum ion, the zinc copper or the aluminum copper battery. But just in general, what happens is there's going to be a cathode and there's going to be an anode. So an anode, it is going to give up electrons. Okay, you see the electrons leaving the anode and going to the cathode, and the cathode, it wants those electrons. It's actually going to take them in, and so the reason that is because we'll talk about later, these electrolytes, the cations, are going to be pulled to the cathode because we're getting positives there. negative electrons like positive, so they're going to continue going to where the cations are, where the positives are. Whereas the anode, it's going to become a little bit positive once it loses its electrons, and that is because it's a little positive, is going to attract the anions. So they become negative. So the anions go to the anode, where they're going to make it negative, and the cations go to the cathode, where they're going to make it positive, and that's going to create what's called a voltage, a push, which we're going to talk all about. But more than anything, these electrolytes are just the ions in a solution. They're going to go to the various sides, and they're going to drive the electrons to want to move through your circuit. So we talked about voltage. You've heard that word voltage before, 9-volt battery, maybe. What does it mean? Well, electricity, you can think of it like a water hose. So the voltage is like the pressure inside that water hose or the wire. Like how much push is there to get it through. Now, current, you could think of it like the size of the hose. It's basically how quickly it goes through. And resistance, this is like stuff in the way of the water, like it's slowing it down. So the voltage, it's going to be kind of determined by how quickly things can get through and how much stuff is in the way. And that's going to be lead to more pressure, meaning a higher voltage. The more voltage you get, the more the pressure pushes electrons in electricity compared to water in a hose. So I want you to think to yourself, okay, what is voltage in your own words? All right, hopefully you were thinking, okay, it's like the push of electrons, because that's really what it is. Okay, so what you made in your lab was something called a voltaic pile. I'm going to talk about how this is the really the earliest battery. So what you did is you had copper and zinc. Your copper was down in the bottom. That's the penny, right? And then you had zinc and originally aluminum up on top. So the way it really works, okay, is you connect a battery or you connect a multimeter or you connect a bulb like we saw, okay? And when you do that, you give a path for electrons to flow. So zinc, especially, and you should have gotten a better battery with your zinc. Zinc is okay with giving up electrons. It's actually quite stable. And those 2 electrons at the 4s level, which we're going to talk about, 4s2 electrons, they're happy to leave the zinc, the anode, and they're going to go to the cathode, which was actually the positive electrode, in this case, copper. Copper is pretty close to full, so it's pretty happy to accept electrons at its 3D. So electrons want to go, right? And they will go from the anode to the cathode if they can. But if there, wasn't a typical battery, it would just happen real quick and then it'd be done. But the game changer is those electrolytes. So when you have electrolytes, and you may have used a sports drink, may have used juice, you may have used sodium chloride, the salt water, coffee. There were many, many sources of electrolytes. They're going to have those positive and negative ions. And because electrons leave here, remember, electrons have this negative charge. So if you have less negative, that actually makes you positive. And so what's going to happen is the electrolytes are going to start moving to the anode, the zinc or the aluminum. And because all the negatives are going there, that makes this side negative. Okay, and that's why it's the anode. Those negatives moving there allow it to become more and more negative. Now, on the positive side, again, it gets electrons, so it becomes slightly negative here. Because it's slightly negative, now we've got the positive cations that are going to move here and make the cathode positive. Down here, it's just the negative ions that are all in this membrane, all in this solution here, moving here. And as long as the negatives are lining up here and making it negative, well, negatives push negatives away from each other, so that's going to push more electrons out. And then positives accept electron, negatives like positives. So as long as this becomes more positive, it's going to move those out. And it's going to move like this and keep doing this and sending out electrons and down here to the cathode until all of the electrolytes are all lined up. They start all mixed up, and then eventually they will get basically plated to one side or the other, meaning they're like all to their respective sides. So all of them end up on the all the negative anions end up here. All the positive anion or positive cations go down here. And when it's all spent, then the battery is done, unless you can recharge it, like with a rechargeable battery. Now, I want to talk about the history of the battery. So around the year 1800, that's when Alessandro Volta, oh, look at that, probably rings a bell, created this first battery. So it was zinc copper. It's one cell, sometimes called element, is one copper, one zinc, and then that membrane in between with the electrolytes. And he just had zinc, blotted some paper with salt water, copper, and then as he added more and more and more and more, he got more and more and more voltage, which allowed him to create the first battery. So maybe you're thinking like, well, why would it do this? Well, zinc, you can see, we've talked about this is a Bohr model, but we've got orbital diagrams. And if you look at good old zinc here, you'll note it's got these 2 electrons in the 4th level, right? But then it's really full. It doesn't only have the 8 valence electrons, but zinc actually has a full 3D as well. So it's a full shell or orbital diagram. You see all these 3Ds, the 3s, the 3p, all of these added together are nice and full. So because it is so stable, it is so full underneath, it's pretty happy to give up these 4s electrons. Now copper, if you compare it, it actually has 2 valence electrons here, but it's got 1 less electron in its D, right? So it is okay with that, and actually this 4s sometimes falls down to the 3D level, but it can fill up more. It is not nearly as stable. It will take electrons from zinc, which is happy to give them to get that stable level, and copper becomes a bit more stable when it gains that 1 more electron. So ask yourself again, why does zinc give up electrons to copper? Oh yeah, it's because zinc has that nice super duper mega full 3 level, right? Those 3Ds are filled, and so it can give these up pretty easily. And copper, because it's so close, just missing the 1, it's happy to take those electrons. So in general, if something is more reactive, it is happy to give electrons to something that is less. So we have zinc that's pretty happy to give up its electrons to copper. It is so comfortable down there at that 3rd level that it's happy to give its electrons to copper. So we made a wet cell. Okay, it wasn't contained. We added a liquid onto the membrane, and as such, it was called a wet cell. But most of the batteries you're going to interact with every day are called dry cells. They're in portable devices, flashlights, calculators, your phone, if you have one. Uh, Most of you do. That's all dry. Okay. Um, and with dry cells, um, they are going to have a case around it. There's also instead of having just liquid sloshing around in there, usually the electrolytes are in something called a paste or a gel. Things move a little slower. The anions and the cations move a little slower, so that can delay the battery being used as quickly. Um, and that's another benefit is that most common dry cells, like an alkaline cell, like your AA batteries, your Duracell or Energizer batteries, are used because they're inexpensive. They put out fine electricity. They can be stored on a shelf without breaking down. They're reliable. They're leak resistant, and they just work better for most needs. But we used electrolytes, and we use zinc and we use copper. But different dry cells can have different things. They can have manganese oxide, zinc chloride, lithium. These are all electrolytes or metals that could be used. And again, remember it's paste in a sealed case. They're that way, so they can be placed in any position. You can turn a battery upside down, and it's not going to be a problem. You can set it on its side, and it's not going to be a problem. Which is why dry cells are usually preferred. But there are wet cells, like a motorized vehicle, a car battery is a wet cell. It uses a liquid electrolyte. It's usually an acid like sulfuric acid, H2SO4, and it allows for really fast usage of the electricity. Um, they are oftentimes cheaper and easier to make, but they're not as safe and they're highly corrosive, which is why the dry cell can be a better cost, especially if it's smaller. But it's dry cells much more reliable than a wet cell in a lot of environments. And that's really all I wanted to tell you. Really, you should understand when you're describing batteries how to draw a diagram of your battery. What was the cathode? What was the anode? Where are the electrolytes? What are the electrons doing? Make sure you're drawing the light that lit up. Uh, Explain what a cathode is. The side of the battery that becomes positive because the electrons go there and it attracts the cations. Make sure you can say what an anode is. Remember, it becomes negative because it's losing electrons, and the anions are going to go there. You should know what the electrolytes mean and where they're going to go. And you should also be able to talk about how electrons flow, how they go from the anode to the cathode, because the cathode, like copper, is happy to accept electrons, and zinc and aluminum, to a lesser degree, is happy to give up electrons. That's why they're the anode. So know those things, and you'll do great. I look forward to seeing how you can do. Let me know if you have any questions.